Okay, this session we're going to learn about covalent bonding or covalent bonds. First of all, let's have a look what we mean by covalent. So covalent is made up of two parts, the word. Co comes from the fact that one thing has to do something with another thing. In this case, two atoms are working together. Just consider the words cooperate. If you're cooperating with someone, you'd usually you and another person who are working together. If you coexist with someone, you are usually living alongside another person. If you are codependent, you tend to have two people relying on each other. In this case, we're talking about two atoms, hence the term co. And valent comes from the fact that we are talking about valence shells. Okay, so this is the outermost electron shell. So co, together, and valent, referring to the valence shells. Okay, so covalent bonding involves the valence shells of two atoms. The goal, again, is that when a reaction happens, the two atoms that are involved, and in a reaction mixture there will be millions of these, not just one pair of atoms, but we're going to consider one pair of atoms. The reaction that happens has the ultimate goal of being able to achieve a full valence shell for each atom involved. And we would term this as gaining, I can't spell, gaining a stable electronic configuration. And what we mean by this is that the outermost shell is going to reach the maximum number of electrons that it can hold, the first shell being 2 and each subsequent shell being 8. Covalent bonds occur between non-metals only. Okay, so for example, hydrogen and chlorine. Let's look at that particular example. So hydrogen has 1 electron, chlorine has 17 electrons. So let's draw the electronic configuration. So hydrogen, 1 electron, goes in the first shell, that's all it has. Chlorine has got 3 shells, so period 3. The first shell holds 2 electrons. The second shell holds 8 electrons, so that's full. And then the outermost shell, the valence shell, holds 2, 4, 6, 7. So hydrogen's electronic configuration is simply 1. Chlorine's is 2.8.7. Neither of these has its outer shell full of electrons. Hydrogen needs to add another 1 to complete that first valence shell, which can only hold a maximum of 2. Chlorine needs to add another 1 to complete its outer shell, turning that 7 to an 8 electrons and achieving a full outer shell. So if we're talking about two atoms working together, these two valence shells are going to work together. And to show that the type of bonding and that they are working together, we overlap the orbitals, because in covalent bonding the electrons are shared. Okay, sharing of electrons. So hydrogen's electron is in this orbital. 2, 4, 6, 8, 2, 4, 6, and 7 in there. So the hydrogen bonded to our chlorine. The orbitals overlap, and the result is that hydrogen
now has 2 electrons. It's donated one and chlorine is donated one. They've shared those with each other. So the outer shell, the valence shell of hydrogen, is now 2. And chlorine has, in its outer shell, it's shared its 1 electron and it's borrowed 1 from hydrogen. And the result is that in that overlap, that sharing of electrons, its outer shell is now 2.8.8. So both of them have achieved a full valence shell. They've both achieved a stable electronic configuration through the sharing of electrons. Now, because electrons don't actually get donated, neither hydrogen or chlorine lose an electron. They're simply overlapping their orbitals and sharing that electron. There is no overall charge associated with this as there is in ionic bonding. So they cannot conduct electricity. Oh, why can't I spell? Electricity, sorry. Long sessions. Okay. The points also we need to know about covalent compounds, okay, is that these covalent bonds are very strong. They're strong because this layout is favourable. Achieving a stable electronic configuration is favourable for both atoms. Therefore, that bond is very strong. However, between the covalently bonded atoms in a molecule, the forces between them are weak. So let's consider water, for example. So water is H2O. Each oxygen bonds with 2 hydrogen atoms, and we have a very strong covalent bond. Now, if you had a glass of water, you would have millions, billions, trillions of water molecules in that glass of water. Between each of the water molecules, there is what we know as intermolecular bonds. And again, looking at this term, inter means between, and molecular refers to molecules. So between molecules, there are intermolecular bonds, and these intermolecular bonds are very weak. Now we know that when we change between solid water, so ice, to a liquid, to a gas, we either have, in the case of water, an ice cube, a glass of water, or you have steam. In each case, the water molecule stays intact. To change between these states of matter, it is this intermolecular bond between molecules that is affected. In moving from solid to a liquid to a gas, these are broken. Enough energy is being put in to overcome these bonds until you ultimately add a gas where these bonds do then not exist. And then if we remove energy from the gas, it condenses again from the liquid. These bonds are continually being made and broken as the molecules slide past each other and roll over each other. And then if we remove even more energy, these bonds then are strong enough to stay in place. There's not enough energy to overcome those bonds, and the water molecules are essentially frozen into place. Okay, so the key takeaways from covalent bonding. Covalent bonding involves the valence shells of 2 atoms. The electrons in the outermost shell are shared between these 2 atoms to ultimately gain a stable electronic configuration. Because they each achieve a stable electronic configuration, these covalent bonds are strong. Because there is no transfer of electrons, only sharing, covalent compounds, cannot conduct electricity. It is important to understand that simple covalent compounds have low melting and boiling points. This is because even though the covalent bond between the atoms in a molecule are very strong, between the molecules there are intermolecular bonds which are very weak. And it's these bonds that are affected when changing state. And the change of state is what is needed to melt and to boil a substance. So when you change from a solid to a liquid, your melting point for water is low, it's 0 degrees, because it only takes a small amount of energy to break these bonds, give it enough energy that these water molecules can continually break and make as they move throughout the liquid. And then we apply a little bit more energy and we can overcome these completely, and a gas is formed where the water molecules are free to move. You never actually break these covalent bonds because they are very strong, but the boiling point and the melting point are low because of the intermolecular forces, which are weak. And there we go. Have a look at some examples yourself. Try recreating this diagram and choose some other non-metals to do the same. If you share 2 electrons, then the result is a single bond. Try drawing out the covalent bonding in water, H2O. Show the covalent bonding for water using this explanation. And a challenge question would be to have a look at the bonding in carbon dioxide. My clue with this one is that 2 electrons, a pair of electrons being shared, forms a single bond. If you share 4 electrons, 2 from one atom, 2 from another, then you can get a double covalent bond. Have a go.